In single variable calculus, you have u substitutions. So basically, it's making a neat little substitution to cancel some things out. So let's say we have 2x minus 3 over x squared minus 3x plus 1. We're taking the integral of x. Well, we could say, well, let's let u equal x squared minus 3x plus 1, and then we compute the derivative of that. Du is 2x minus 3 dx. So then du over 2x minus 3 is equal to dx. Plug that in, and we get a new integral, a square root of u. And then these terms are just going to cancel, and then we know how to do that, and that's really pretty simple. Well, I mean, kind of. We just take, we just do that, and then use the power rule, and yeah. So anyway, to move on, multivariable change of variables is like the u sub, but on steroids. So this is like the 4th time now that I have tried to do this problem, and I keep messing up. So when we do this, we're going to have an integral. We're going to have, for this example, we're going to have the double integral sine of x minus y cosine of x plus y over the region dA. And dA is this region in xy plane, of course. And it's going to be y is equal to pi, y is negative pi, and x is pi. So it's this triangular region that I am doing backwards. This way. It's this way, not the other way. This way. Okay, so we're going 0 to pi, and 0 to pi negative pi. So pi negative pi, and pi. And this is, we're going to call this region R, and we're going to transform. We're going to be using the variables u and v, and we want to know how we're going to draw our new region. But first, what we're going to do is we're going to make the substitution. U is equal to x plus y, and then v is x minus y. So now the next step we're going to do is we're going to add them together and subtract them together, because we want to solve for x and y in terms of u and v, because that's going to help us with figuring out our Jacobian. So u plus v is equal to x plus y plus x minus y, which is 2x. U minus v is x plus y minus x plus y, and that's going to be 2y. And that is almost sufficient. 2x is equal to u plus v. X is u plus v over 2. 2y is u minus v. Y is u minus v over 2. So back to this. We have our variable u is equal to x plus y, and v is equal to x minus y. We start with our first point, 0, 0. 0 plus 0 is 0. 0 minus 0 is 0. So we're going to have 0, 0, 0. Now, pi. U is equal to pi plus pi. So we have 2 pi. v is equal to pi minus pi, so that's going to be 0. So we have 0, 2 pi comma 0. And then for our third point, we have pi negative pi. So u is x plus y, so pi is, okay, so pi plus pi. Pi plus negative pi is going to be 0, and then pi minus negative pi is 2 pi. So we have these 3 points, and then it's going to be bounded by this line, because we want to connect all the dots, connect all the points. And then we're going to call this region S, bounded by this region. So when we write this, we're going to have u is going to go 0 to 2 pi. V is going to be a little bit trickier. We're basically using the equation of a line that goes from 2 pi to 2 pi kind of. But basically we're going to have v is going from 0 to 2 pi minus u. So that's going to give us our limits of integration. So next step is we're going to compute our Jacobian. So our Jacobian is going to be our matrix of partial derivatives. So this is partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. This is 1/2, because when we differentiate x with respect to u, this is 1/2, and then 1/2 for v also. And then when we do y, 1/2 here, and then negative 1/2. And when we take the determinant, we get negative 1/2 times negative 1/2. Oops, I think I might have had a double negative there maybe. 1/2 times negative 1/2 minus this term, 1/2 times 1/2. That's negative 1/4 minus 1/4 is equal to minus 1/2. But when we use a Jacobian, we use the absolute value, and that's equal to 1/2. So now we're ready to set up our integral. We have our integral from 0 to 2 pi, and then our integral from 0 to 2 pi minus u of sine of x minus y, which was v, and then cosine of x plus y, which was our u. Let's put those in parentheses, times the absolute value of our Jacobian, 1/2, and then our dA. In this term, it's dv du, because we're integrating with respect to v first. So we can then rewrite everything. 1/2, remember our Jacobian is our scaling factor, so 1/2 2 pi cosine of u, 0 to 2 pi minus u, sine of v dv du. And we're going to do this inside part first separately, because we're going to multiply it all out anyway. So let's 2 pi minus u sine of v dv, and this is equal to minus cosine of v from 0 to 2 pi minus u. Now this is going to give us minus cosine of 2 pi minus u minus the negative cosine of 0 and we can use the identity that cosine of 2 pi minus u is equal to the cosine of u. So this is just cosine of u plus the cosine of 0, which is just minus cosine of u plus 1. And then we're going to plug that back into our original integral. So now minus 1/2, 0 to 2 pi cosine of u times 1 minus cosine of u du. And this is just 1/2 times integral of cosine of u minus cosine squared u du. And then we can also just cancel this term because the integral of any trig function is equal to 0. So that just gives us 1/2 0 to 2 pi minus cosine squared u du. So the next step we're going to do is use this identity, cosine squared u is equal to 1 plus cosine of 2u divided by 2. If we take the negative of that, we just get the negative of that. So that's going to give us the integral 0 to 2 pi 1/2 times negative 1/2 du plus integral 2 pi cosine of 2 pi du. And just as before, we're going to cancel that term because trig function. So this gives us 1/2 well, let's just pull the negative 1/2 out here. So minus 1/4 u from 0 to 2 pi and that's our answer, minus pi halves. So it was kind of a long one. So we started with this. We started with the u sub, basic u subs, and then we had our problem. We changed our coordinates from r to s, and we found out what our new bounds were. 2 pi, 0 to 2 pi, and then 2 pi minus u. We had u as a substitution, v as a substitution, and then we had x and y, and we solved them for in terms of u and v. We found our Jacobian, and then we did our integral, and when it was all said and done, we ended up with, that's a really ugly pi, minus pi halves. Anyway, thank you for watching. Bye-bye.